we are going to start the afternoon session, and our first speaker is Michael Huff. He has been involved in fabrication at the nano and micro scale for a number of years. He has been, nobody has to say the number, but a number of years. He is with what's now MNX, but I think began life as MEMS Exchange, and so he has spent much of his career devoted to developing resources and infrastructure to enable high-quality manufacturing on the micro and nano scale, and he is going to address nanosensor fabrication, some of the practical issues that are involved. There's going to be followed by a couple of talks from Abhishek and Susan, which will be much more about testing, and then Sammy is going to speak, and then we'll have a break before convening back again for what will be more of a discussion panel, discussion for the whole room as opposed to just a panel. But I want to start by inviting Michael to come up to begin the afternoon. For I think is going to be a really excellent talk to address some issues that we didn't quite get to this morning. So thank you.
Well, thanks. I think I'd rather be here than where Attorney General is this afternoon. So sorry for the politics. So yeah, I spent a lot of years doing fabrication work, and so I'm going to kind of focus on, in fact, I was asked to focus on some issues related to fabrication that I hope will be useful to people. I've taken a long time to learn these things, and I'll try to convey as much as I can in a limited amount of time. So I won't spend a lot of time on this because I think you guys probably know as much about this as me, but nanosensors, new breakthrough technology. Where I kind of view it is, where you got these multifunctional materials and merging them potentially with integrated circuits, and where that gets interesting is you get the perception capability of different types of sensors, integrated electronics. So the sensors are sort of like the eyes and ears and nose, if you will, and the electronics are sort of like the brain. So that's a kind of a powerful concept. And I threw this in for kind of the roadmap of integrated circuits, of course, Moore's law, which sees this just dramatic increase in the number of transistors that we can put on each slab of silicon. And of course the decrease, we're really talking about nanotechnology now with integrated circuits. Some people call it microelectronics, but it's really a nanotechnology because the gate widths are on the order of 10 nanometers. And up to the present time, like this Moore's law, the integrated circuits has really measured their progress based on how many transistors they can put on a single slab of silicon. That's starting to change, I think, and it's changing in important ways because it's now becoming how capable the chip is. What does it do for the user? How does it influence the environment? Things like that. How does it enlighten the user? And of course we have the Internet of Things, which is where not only have these microchips and nanochips that can sense things about the environment, process the information, store the information, but also communicate with other things and other entities out in the environment. So that's a very kind of interesting concept. A lot of these technologies leverage heavily from the semiconductor manufacturing realm. And it's the kind of integrated circuit processes that people use to build electronic devices. So if you kind of look at, I have to see, is this the laser?
It's on the bottom, yeah.
Is it on?
Yes.
Oh, okay, I see it now. So if you kind of look at the cycle of events here, you typically do a deposition of material, pattern transfer, photolithography, removal of material by etching, and you kind of continue this cycle over and over again. And then once you're done, depending on how many photolithography steps you have, then you do testing, sectioning, and packaging and testing and things like that. So all that's nice and fine, and we leverage for these kinds of technologies heavily from the integrated circuit world, the kind of standard processes that you see in any integrated circuit foundry operation. And we combine that with, of course, now these very exotic sort of things, like exotic material depositions or exotic material etches and wafer bonding and nanomolding and things like that. So we're kind of leveraging this pre-existing, well-developed, mature, existing technology base of integrated circuits whether we're using integrated circuit foundry or not, that's kind of not the point. The point is we're using that equipment set, those sort of technology types. And we're combining that with now these new kinds of things that allow us to make nanomaterials and nanostructures and things like that. So I think it's kind of useful to go through and kind of highlight some of the differences between this mature technology of integrated circuits and this, frankly, less mature technology of nanosensors. So integrated circuits have three basic mature device types: transistors, resistors, and capacitors. That's all there is. So it's pretty simple, and they're wired up differently to form different kinds of circuits and stuff. You get into nanosensors, and it's all over the map, and almost any kind of thing. They could be chemical sensors, biosensors, mechanical sensors, and that's a high-level description because you can get in all different types of each of those sensor categories. Integrated circuits have very standardized process technologies. So there's a thing in the industry, in the integrated circuit industry, called process technology. That's kind of a manufacturing process that's used in production, and it might be 20 or 50,000 wafer starts a month. A process sequence is something that is more appropriate to prototyping or a one run, one up kind of process, where it's obviously not in production and not nearly well developed. So the integrated circuit industry has standardized processes like CMOS and memory and stuff like that. But you look in the nanosensor world, and the process sequences vary greatly for the different device types. There's no standardization for any practical purposes, and they're almost always completely customized in terms of the processing steps and the ordering of the processing steps. Integrated circuits have a standard set of materials and processing techniques. Nanosensors uses a much wider diversity of materials and processing techniques. Integrated circuit foundries are kind of one-stop shopping. Everything you need for making them is under one roof, where for nanosensor fabrication, the core competencies in commercial foundries is very limited, if it even exists at all. And it's limited to what's useful for IC manufacturing. So therefore, the design and process freedom for building nanosensors could be very, very constrained. Integrated circuit foundries are easy to access. There's really kind of two models. One is kind of self-producing model, sort of like in the Intel, where they have their own foundries and they produce the microprocessors. And the other model is like a TSMC, Taiwan Semiconductor Manufacturing Corporation, where they have a standardized process and people just send them the designs and they manufacturing no matter who they are. Access to nanosensor fabrication resources can be difficult and expensive, and you need a very detailed knowledge of how to make good decisions about what foundry to use. Integrated circuit industry is very capital intensive, many billions of dollars to build these foundries. And like I said, dedicated in-house foundries or outsourced foundries work well depending on the circumstances. Most of the nanosensor markets are so small, the low volume manufacturing, that it's not only a capital intensive business, but dedicated in-house fabrication resources are probably not economically justifiable. So I'm going to talk about development of these kinds of devices, and I'm going to mainly focus on MEMS. And the reason I'm going to do that, I know it's a micro device instead of a nano device, but the fabrication technology is very similar, and I think we have much more experience with MEMS development of sensors than we do for nanosensors. There's just not a lot of track record built up for nanosensors that have gone through the science, the development, the prototyping, and into production to really know how long these things will take. So what I would tell you, though, up front, I think the MEMS is probably easier than the nanosensors would be. So this is probably putting the best spin on what you're looking at, okay? So for MEMS development, what we normally see is about a concept phase of 6 months or less. This is where the brainstorming is going on, and some design and engineering will be going on, analytical stuff like numerical analysis, finite element, things like that. And then it goes into development phase, and this is where the trouble starts. And the trouble starts with designing and building customized process sequences that actually yield, okay? And that can take more than 8 years, and I'll show you in the next chart some real-world case real world case studies on how long it takes, and then you get a transition to production. So the bottom line is it's been very difficult for these kinds of devices, these customized sensors that use customized process sequences to leverage already existing fabrication capabilities. So let's say I go to a foundry, they're building some sensors, and they have all the capability for building that sensors, and I go, hi, I've got a new nanosensor I want to build, and I'd like to use your production line. I'm sure they're willing to talk to you. The problem is that it's like trying to fit, you know, a square peg into a round hole. They typically will not have any experience, probably don't even have the right tool set for what you're trying to do in your particular case. There's these differences that come into play that can be real problems to overcome. So this is a chart I created a while back, like a year or so ago. And what I was trying to look at is different types of MEMS devices, and they're listed here, the companies that develop them, the application areas for these devices, and again, these are all MEMS, and whether they're integrated with electronics or not, okay, and estimated time to development, and estimated cost. For obvious reasons, some of the companies haven't been willing to disclose how much it costs to develop these devices, okay? The thing that kind of stands out to me is this right here. I mean, everything is pretty much over a decade, okay? And in some cases, like the TI DLP chip, that's actually more than 20 years. We're talking over $1 billion. You can imagine if you go to a VC and say, I got this great idea, and all it needs 20 years and $1 billion, and you'll get your money back plus something. It doesn't work. So again, this is for MEMS devices, and I expect that this is probably a more positive story than you'll see. So the bottom line is, even for large volume markets, returns on investments are not attractive. And this is an important thing. Just to give you an example, analog devices. They spent $500 million on that airbag accelerometer, okay? Took them 12 years, really 15. They still sell those devices. Their yearly annual sales are about $230 million, okay? Now, that's sales revenue. That's not margin. So if you look at where they're selling into the automotive market and consumer electronics and stuff like that, they might be able to get, I'm going to be very generous here, a 20% margin, okay? 20%, that's probably way too high. So let's say they're getting 20% on a $250 million market. That's $50 million a year. 10 years just to pay back the development cost, not including the cost of money. That's not a good story for from an investment standpoint. And there's a lot of similar stories with all these, okay? So let's dig a little bit deeper and look at some of the problems here which causes this. And I call these the usual suspects. So these are the criminals that steal from us. And there's more criminals than this, and I'm not showing. So these are ones I'm just going to highlight. In fact, I'm just going to really highlight 3 of them in the sake of time here. The process integration, the tolerances, and material properties, okay? So process integration, what does that mean? That means I've got process step A, process step B, might be a thermal oxide growth, the nitride deposition, a photo, each of these processing steps. In order to make something that's manufacturable, I've got to get all those processing steps to work together so I have yield at the end. And typical yield numbers for the integrated circuit industry are 95% or higher. For the MEMS industry, they vary from that high down to 5%. So it really depends on what you're doing. And if you're selling to the military like we do, we can get away with a 5% yield because they'll pay a lot of money for these specialized devices, okay? In the consumer electronics world, forget it. They want a 90% yield. They want these things like jelly beans cost. So the process integration is getting all that stuff to work, but to get the yield, and to meet my performance specifications as well. So the yield number is just not whether the device works or not. It's got to meet the performance specifications for the intended application. All right? And I'll talk a little bit more about that. And this is where most of the development happens and most of the money is spent, is developing these process sequences, doing the process integration work. Relative tolerances. I cringe every time I hear somebody from my community say that these technologies give you high precision. It's not true. It's the reverse of that, okay? I'll give you an example on this slide. So let's say I'm making a metal interconnect here. So I got a pad, and just a line of metal between the two pads. Okay, pretty simple. And let's say the feature size is 1 micron. So that's the width of that device. And I could do that at a tolerance of 0.1 microns. That's probably a fairly good spec for a contact lithography process. So if I look at my relative tolerance, which is the amount of variation I have divided by the width, it's 10%. That's a big tolerance. Okay? Now if I compare that to conventional manufacturing, so let's say I go over to Reston where I live, and there's a machine shop near Dulles Airport, you know, with CNC machines. And I talk to the machinist in there and I say, well, I want to make a 4-inch diameter shaft, and what can you make that to? And he says, easily with my eyes closed and having a, you know, a banger the night before, I can do within 1 mil, plus or minus a mil. So you do the math on this, 25 microns divided by 100 millimeters, 0.0254%. You can see the difference here. Now if I just divide the two, it means the semiconductor manufacturing, at least for this device, is almost 400 times worse on the relative tolerances. It's amazing anything works, isn't it? And it gets worse as you get smaller. Those tolerances go up. So here what I've done is I've plotted the relative tolerances. This is a logarithmic scale here in percent. Typical feature size, so we start 10 to the 8th down to 1 nanometer. And on this scale, we've got relative costs. So there's 2 curves here, green for the cost as things get smaller, and a red line for how the relative tolerances go as things get smaller. So we can see on here some data points. These are data points for going to that machine shop over at Dulles Airport using macro scale machining techniques. And this is kind of relative tolerances I can get. If I look at you know, what I'm doing with contact litho and RE etching, and let's say I'm making something that's on the order of, you know, 10 microns or something like that, I can get a relative tolerance of between 1 and 10%. Okay? So I'm talking about a line width, not to confuse you with that previous example, but a line width that's a little bit bigger than that 1 micron. Okay? So more of a MEMS type of thing. As I shrink the size, though, down, let's say I go to an I-line stepper lithography, RE, on, say, a polysilicon layer, I get to above a 10% tolerance, and I go to E-beam with RE, and I get maybe the same, but my cost goes up. So the point being that the tolerances get higher as I get smaller as a typical function, but the costs go up. So you can see from the machine shop here, you know, I've got a cost level that's down in maybe $100 per, you know, let's say normalized to $100, and then when I go to some of the advanced nanotechnology or integrated circuit technologies, I'm you know, somewhere between 10 and 100 times higher. So the cost goes up very significantly. But there's another point to this. And the other point is something that people sometimes miss, and that is you got to be careful about the physics involved in a device too. And what I mean by that is if we can look at the power relationships of the equations that define these devices. So the nice thing about digital electronics, and the reason that they work so well, is because they're simple switches, they're on or off. So they're relatively forgiving for tolerancing issues with regard to the gates in these devices. if you're old enough to remember, as I am, the early days of integrated circuits when we had analog integrated circuits, they were a real pain to deal with, and everything had to be trimmed because the manufacturing lines could never keep the tolerances well enough that the devices would actually work. So we developed these, kind of standardized processes for laser trim resistors and things like that. Well, when you get into these mechanical sensors, the same thing happens. The tolerancing issues start to burn you again. So the point being that electronics that are digital work very well, but when you get into these sensors, whether capacitors, filters, resonators, whatever, they can go to the second power, the third power, fourth power, or whatever. So I've given a kind of example here. This is a microfluidic channel, and people probably recognize this equation. For the flow rate is equal to the radius of the flow conduit to the fourth power, differential pressure divided by 8 times the viscosity times the length of the channel, all right? So looking at this R value here. Let's say the R value varies by 10%, plus or minus 10%, okay? What that means is now that I have a 40%, plus or minus 40% variation in that flow rate Q. So the physics really matters here. And I might have some variation in the length of this channel too, and that will come into play. So you have to look at the defining equations for these devices and then kind of back out how all my relative tolerances affect my device performance and my yield. This is looking at the yield equations, okay? So I've got my device kind of shown up here in a plan view with a W as before. And let's say my critical dimension is that width of that beam. This is a freestanding beam, let's say. And when I manufacture that, I'll have a Gaussian distribution. If I have a real sloppy process, I'll get a Gaussian distribution, which will look pretty wide. But if I have a really tight process with small relative tolerances, the Gaussian distribution will be really narrow, right? And you can define this according to, some equation. But it's further compounded by the device physics. So let's say I build a device up here, and it has this statistical distribution. But let's say it goes as to the W to the second power. I'll just make that up. What that means is now this distribution doubles in size, okay? So you got to keep that in mind. Where that matters is going over to the right side, there's an acceptance range. And this is the acceptance range based on the device's performance to meet the requirements for whatever the application is. And that's usually defined by some kind of step function like this. And now you have to look at the intersection between the acceptance range and your statistical distribution, and you get an equation shown down there at the bottom. So looking at this in kind of simplistic form, you typically have two kinds of things going on. So let's say this is my statistical distribution, and my acceptance range sort of superimposed on that. And what I'm looking at here is I've got a bias error here, and I've got a random error set by whatever the Gaussian is, right? But I'm looking at what my yield is, which is the intersection of these two, and it's only this stuff at the tail. So in other words, I've got a pretty crappy yield here, right? Now, I can remove the bias errors pretty easily. I can change the mask designs, just change the dimensions. If I know how much my etching processes might be affecting my offsets, if you will, in the tolerances. So I can move this acceptance range over on top of the statistical distribution pretty easily by changing the mask set. And people do this all the time. But you can see still the problem is my acceptance range is only so narrow and the statistical distribution is much, much wider. So the yield's gotten better, but it's still pretty bad. Really what you want is something in this situation where I got an acceptance range and my statistical distribution fits in nicely in that acceptance range, okay? And these small made devices, again, typically have large spreads in their distributions. Material properties, okay. So this is something that we face daily, which is you deposit thin film materials and the material properties are not only not very well controlled, they tend to vary depending on what other process steps might be done after you deposited this material. So if I put down a layer of material, and let's say it's got a compressive stress in it, and I want that compressive stress to be a certain value, life's great. The only problem is I probably have multiplicity of processing steps that follow that deposition of that thin film material, which then can affect the material properties. And particularly any kind of thermal steps will radically change those material properties and can change it even from going a compressive stress to a tensile stress or vice versa. So we tend to focus on stress issues because that's the more important one for things that have any kind of mechanical functionality. It also affects the electrical behavior, though, the stress levels in these thin films. And it has a huge effect on the device behavior and, of course, affects the resultant yield. And other things can happen, like, you get not just the yield loss and poor reliability, but it also increases development times and costs and stuff like that. So what can you do? So I've kind of painted, what may be seen as a dreadful picture. I don't mean it to be that way. I think it's more of a realistic kind of picture to know what you're getting into. So recommendations, and this is coming from a lot of time spent pushing wafers through the fabs. You want to keep the device design and manufacturing process as simple as possible. Nothing is worse than getting caught up in a complicated process that's not going to work for everybody. And a lot of times the process, the designs on these things tend to be a little bit overcomplicated, if not a lot. In the MEMS industry, there used to be a lot of people who wanted to, merge kind of the most advanced electronics with sensors, and that was always very difficult. And I think for the most part, people have kind of given up on it, at least where the state of the technology is, because trying to deal with where a 10 nanometer gate is even located on a chip is a problem. You can't even find it, much less connect to it. Consult early with industry fabrication experts on developing manufacturing processes, and that doesn't mean the guy in the EE department who runs the lab at your university. Sorry, but this means somebody who actually has to do stuff for production and lives or dies every day on whether the production line can meet its cost goals and satisfy customers and stuff like that. I want to stick to already developed process steps and technologies to the extent possible. So I know that a lot of you guys are thinking about exotic materials and things like that, and I understand that. But for everything else that you don't need to make your device, stick to standardized stuff. And this is very important. Determine if the resolution and relative tolerances of the tools and processes are going to be able to get your yield numbers. I try to get people to think about this who are doing development and prototyping and trying to transition to a point where they can get into production. It's always difficult to convince people to do this because they have to spend money on it, but it's well worth the effort. It's hard to get venture funding on a lot of these kinds of enterprises these days because there's a bad track record with this. But if you do get venture funding, they're going to push hard on this. And the reason is because they want to make sure that they don't get burned, because they've gotten burned in the past. And you may need to perform some fabrication experiments. And the reason being that if somebody said, well, Mike, what's your relative tolerance on such and such a process? And I go, it depends. And that's not the answer you want to hear, right? But it depends on what exactly you're trying to do. So you may have to go in the lab and do a part of the process in order to determine. I may have the number for etching a 1 micron thick film, but if you want a different thickness of film, it doesn't mean that it translates perfectly. So sometimes you have to go in the lab and do these experiments to actually be able to know what the relative tolerances are for the process depending on what you're trying to do. You have to determine how the variation of material properties impact yield. Like I said, these material properties will change depending on the process sequence. Design the packaging as early as possible. I can't tell you how many people have gone through development of these devices and then, as almost an afterthought, say, oh, I need to package this too. And it's a real problem when you're dealing with that, because usually it hits a reset button and you have to go back and do development on the devices, which is of course costly and results in more time being spent. You need to use a combination of methods to develop models. The models must be validated with experimental data. We do not have CAD models in the MEMS world that are multi-physics that have predictive accuracy. And the reason is that, one of the reasons is that the material properties change. So you don't know what the material properties are. So you guess what I think the material properties are. I do my models and I get some results. But it's not until I've gone through the fabrication process that I can measure those material properties, which are dependent on a process sequence, then I can feed those back into my models, okay? Expect to perform multiple iterations on development and multiple design changes. Embed test structures into the layout to determine material properties, particularly on the initial runs. And exercise care in selecting fabricators. Changing foundries is extremely costly. Every foundry will take your money. I guarantee you that. And the big guys, the TSMC, they won't talk to you for less than $1 million. So you can't even get a conversation going. They're also going to be resistant on getting into issues like relative tolerancing and stuff like that, because those become proprietary. They'll have design rules for integrated circuit process, but if you're trying to do something unusual, it's a different ballgame. They might not even know. They need to go and measure it. So the point being that you don't want to change fabricators. So your idea might be great, but it won't matter if it can't be made. And just one little advertisement, since I'm here. So I'll tell you a little bit about MNX. I've been operational since 1999, so almost 20 years. We were started with funding from DARPA to provide infrastructure to DARPA's investments in MEMS technology. A few years later, we started moving into nanotechnology because everybody was making things smaller and smaller. And we do fabrication work for folks. Right now, we have done close to 3,000 different project runs for folks from over 1,000 different customers. So just about everything that you see out there of devices, we've had some helping hand of some sort in. It's pretty amazing. So over the past 20 years, we've had, I think, a pretty big impact on taking these technologies from an idea stage into production. And I can tell you, we're not always successful, but we try. Thank you.
Well, anyways, thank you very much for kicking off the afternoon. That was great. One of the things that we've talked about in this community and in support of this initiative for the past several years is the development of necessary standards. And I think that you touched on that from a processing perspective, that a lot of these novel designs don't have any sort of standard processing. Can you comment on maybe particular areas where you see that might be, reaching a stage where a standard might be,
Well, actually, we were talking about that earlier. So, in the MEMS area, which has been around longer, I could date it probably back into the 70s or 80s. We've tried desperately to get standards. ASTM, SEMI, NIST, you name it. And we've had a couple standards issued. There's actually, I think now 3, 2 of them ASTM for test structures for material properties, okay? It's always been very difficult to get anybody to agree to standards. And, Dorothy was asking me the reason for this earlier, and it's a very fragmented market. That's one of the things. 2 is that the markets are so small that the suppliers of these devices to the larger companies. They can specify what they want, and a small company does it. But that doesn't make it a standard, obviously, right? So one of the things I tried to get to happen, and I would say it was partially successful, this was a semi-working group, probably a decade ago now, was microfluidics, standardized microfluidic connections. Because, if anybody's ever, had to fix something in their, plumbing in their house, they know that piping comes in standard sizes and stuff like that. And it makes sense, because if I went to the hardware store and the pipe didn't fit, it's kind of worthless, right? So, I can know what the size of the pipe is, and these are all based on the physics of the flow through the pipes, obviously, and the pressure loads and stuff like that. So we formed a working group and got a lot of microfluidics experts to work on this. And I can tell you that everybody wanted to go in different directions. It was okay if everybody accepted their standard, but it was not okay if we tried to come up with a generalized standard. And it was kind of like diplomacy in a way, except worse, because you'd say, well, I'll meet you halfway if you meet me halfway, and there was no meeting halfway. So and that's a larger market, much more developed. We still don't have standards. So Dorothy was asking me, what forces this? Well, what's going to force it is if you've got big companies, Apple or whoever, and now they've got a multiplicity of suppliers of whatever devices, they're going to say, I don't want to screw around with your, different design. You either make it this way or we don't buy. So that kind of forces the standardization. And we don't see these markets being typically large enough to kind of have that forcing function on them yet.
Thank you. I think we'll have time for a discussion later, and so any other questions we'll
Okay.
But thank you very much.
Sure.
That was great. And so the